Hi all, I'm Edoardo, and today I'm going to discuss some of our results in the field of secular Lunisolar analysis. Our work, the work that I'm going to present today is a collaboration between myself, Edoardo Legnaro from the University of Namur, and Yannis Gondor from the University of Thessaloniki, and from the details on what I'm about to present today can be found in these two papers. The first one is already published, while the second is. So, let's start by presenting the region towards which we focus our attention, which is the MEO region, which goes from altitudes ranging between 10,000 kilometers more or less to the Circulus orbit. And in particular, we focus on a section between 1700 and more or less 3200. This region is home to various artificial satellites, which are used for navigation, communication, space, environment science. Here I've listed some exponents of the exponents of the GNSS constellations. We have the Russian GLONASS, which is affected by the 2G resonance, and the American GPS, the Chinese Babe, and the European Galileo, which are influenced by the 2G plus H resonance, as you can see on the right with this representation of the resonance by Yannis Gondor. In this domain, friction is negligible. We can model the dynamics within an Hamiltonian framework. And in this region, it's present a web of Lunisolar resonances, which we will see generate large domains of chaotic motion. So, how does this chaotic motion manifest itself? Well, we can see that by changing the phases of the initial conditions, so by taking the same eccentricity inclination, but two different values of the angles small omega and big omega, we will see that one orbit will re-enter in the atmosphere in 103 years, while the other will not. So, the reason why we need an analytic theory is that we can gain the insights in finding which initial conditions will actually re-enter in the atmosphere. And so, this can help us to design a low-cost and large application strategy that exploiting the natural dynamics of Lunisolar resonances, which pump an object eccentricity possibly up until it reaches a domain where friction will start the re-entry, we can indeed design this application strategy. So let's spend a couple of minutes in presenting the Hamiltonian model that we will use. So we consider any object under the gravitational influence of the Earth, the Moon, and the Sun. For the Earth, we just consider the jetting effect, while for the Sun and the Moon, we assume a quadrupolar expansion. It's possible to show that by taking these within the quadrupolar expansion, the difference between taking a circular orbit for the Moon and the Sun and the elliptical one has a difference of less than 0.1%. Then we will take the node of the Moon of the Sun 0, since this assumption is correct for the time span of the satellite problem. Since we are interested in the secular dynamics, we will average out the fast angles to the mean portion of the bodies. And so finally, we end up with a final secular model, which is a time-dependent two-degree freedom model, where the time dependence is just through the lunar node, which is assumed to evolve linearly with a period of 18.6. And this rather compact model has been shown to be sufficient for studying the dynamics of the MEO region, the secular dynamics of the MEO region. Let me just very briefly recall you what Lunisolar resonance is. We have a Lunisolar resonance when there is a commensurability relationship between the average of the G and the longitude of the nodes of the grid and the perturbers. Here on the left, we have the first order and the fourth order Lunisolar resonances, while on the right you can see a theoretical drawing of the resonances. Here up to order 4, and the corresponding FLI max. This is in the inclination eccentricity plane. What we can see is that from the possibly infinite amount of lunisolar resonances one might have, only a few are actually visible in the FLI maps and thus are important for the dynamics. Now, I very quickly want to refer back to previous works. So, this paper by Jean Lacan et al. Of 2016, where they first used an heuristic model to basically qualitatively show that indeed, as the altitude increases, the resonances overlap and generate larger and larger domains of chaotic motion. And also they noticed that by changing the initial angles, the FLI maps change. But so it was an open question how and why we have this change. And also there have been previous attempts in having an analytical model for these resonances. In particular, there is a fundamental work of Reiter in 2001 that by using a simplified model, one could theoretically trace the separatencies, but still we don't have the explanation of why we have this dependence on the angle. So we will try to figure out why. Here I'm showing you a cartography of the Mio region for the region written here on the left. We have the inclination eccentricity plane again, and notice in particular the two resonances with the moon. Here we have the omega minus omega of the moon and the 2 omega minus omega of the moon. As they sweep the phase space for increasing values of the altitude, we have overlap with the other inclination-only lunisolar resonances. And as you can see, with the increase of the altitude, indeed, we can see clearly these larger domains of chaotic motion that are generated. So the steps that we need in order to study a particular lunisolar resonance are the following. First, we choose one. Then we try to build a set of resonant variables that will have a resonant component. Here the action is JR and the angle UR, and a fast component denoted with the letter F. Then we have that using these variables, we try to find a resonant Hamiltonian adapted to the resonance at hand. And from this, by finding a suitable analytical approximation of the fast action and the averaging over the angles, we will find an integrable Hamiltonian. I will not give many details, maybe just a few ideas on this process, but the details are available on the paper if you're interested. So finally, once we reach this integrable Hamiltonian, this turns out to be quite useful in order to understand the structure and the, let's say, the branches that we see on the FLI map of these resonances. It allows us to have a better insight in the eccentricity growth phenomenon, and it's able to accurately predict the width of the resonances in, for example, you can see here the representation in the inclination semi-major axis plane. So, even if I'm not going to give much details here, I just still want to give an idea on the structure that this resonant Hamiltonian will have. You can see that we can divide the Hamiltonian in 3 parts. Basically, we have a resonant part that you can see here, which basically is equivalent to the Breiter analysis. Then you can see that these x and y variables are a kind of Poincare variables, and they are dependent on the eccentricity like this. And since we, in the polar expansion here, we have just the even indices for x and y, you can see that by closing eccentricity 0, the x and y will stay 0 for all the time. So basically, it turns out that circular orbits, the dynamics of circular orbits, are described by this center, that CM Hamiltonian. And so the motion will take place for circular orbits in an invariant manifold embedded in the phase space. And this we call center manifold. And then we have a part that is the mixing of. take a closer look on this center manifold. We have that apart from the region where we have the influence of the moon, here the plots are for the 2G resonance. You can see that the phase space here on the left is foliated in invariant tori, which describe the evolution of the inclination vector around a fixed point, which is this fixed point is a forced inclination, and basically this corresponds to the inclination of the Laplace plane at that altitude. And then, if we enter a domain influenced by either the one-to-one resonance with the node of the moon or the two-to-one, well, we lose the structure and we see the two resonances. This center manifold is quite important because it allows us to understand the role of the angle omega. You can see that basically the choice of the angle omega shifts the whole resonance along the tori, as you can see here. But still, you can see that by changing the angle, even the FLI changes. So still, why do we have these changes, and also what it takes the width of the resonance? So in order to answer the two questions, we need to go in, to find out an integrable model, which we derive by finding an analytical solution for the first part, and then plugging this analytical approximation into the Hamiltonian, and then by averaging the fast angles passed here with respect to the resonant angle, we end up with an integrable Hamiltonian, which is just a polynomial in the x and y variable. This integrable Hamiltonian, first of all, tells us that the lunisolar resonances belong to the second fundamental model of resonance, and also the width in the width of the resonance is given by the region where the center manifold is normally hyperbolic invariant. So also, well, in these variables we can see it's when we have instability of the center point. So now we are ready to understand the structure of this FLI map. First of all, we have these phase portraits that we show here are valid for the eccentricity equal to 0. And then, nevertheless, we have planes in the phase space where the fast vector JF is constant, and this we call planes of fast drift. So we can exploit the existence of these planes to derive let's say, prediction for every eccentricity. Then, yes, FLI maps show the separateness that we see with the integrable model, and let me show you better what I mean with this. So here you can see the animation. Well, the process is the following. We sample some points for eccentricity 0 in the inclination axis. So for each of these points, we have an integrable phase portrait that you can see on the right. And the angle, the resonant angle, the resonance, just gives us the scanning direction of on which we see the separateness in the integrable plot. Then this intersection between the separateness and the scanning direction gives us a value of the eccentricity. And this value is then, well, we follow the fast drift plane up to the eccentricity value given by this intersection, and we draw a point. So you can see that this process gives us the separateness we see in the FLI map. By changing the initial conditions, which of omega and big omega, which in turn changes the resonant angle, we have a different, let's say, behavior in the FLI map, and this is just because we are seeing a different point of the separateness. So, with a static, let's say, wrapping up of the construction, you can see here that we have this prediction here. This is for the, before it goes for the 2G plus CH, here is for the 2G resonance. And again, by changing the initial condition, you have the two branches because then you can see them in the integrable phase. Okay, so this construction gives a very good prediction for, let's say, the more ordered case when the chaos is much smaller. When you are exactly in the intersection with a another resonance, the analysis loses a bit its, say, ability to predict. But you can see that if we have, let's say, the intersection with another resonance is higher, you can see that still you can predict very well the width of the resonance and still have an idea of the development. So now I will briefly touch on the topic of eccentricity growth. So here on the left, you can see an analytical computation of the maximum eccentricity that an object could reach moving along the resonance for the 2G stage resonance. And on the left, it's purely analytical. And on the right, we have a completely numerical computation where for every point here in the inclination omega plane, I take a grid for the other plane elements, and I take the maximum value of the eccentricity reached for each point of the grid. And this gives us these two plots. And as you can see, the integrable approximation gives us the very close picture to the numerical computation. This doesn't explain the dependence on these grid of initial remaining conditions. And we can see that we have a quite sensible dependence on the initial condition. And you can see here on the left the FLI map, which shows the stable manifold of the normally hyperbolic invariant manifold of the full problem. And you can see that the lobes of this manifold and the clinic lobes actually dictate the object lifetime that you can see here. And actually they have a fractal-like structure. But still, for practical application, you can see that we have some, let's say, larger regions of re-entry possibility that are actually possibly exploitable for practical applications. And, now I will finish with this simulation. Here we have a cloud of initial points that are initially a Gaussian distribution. And we can see the transport along the manifold of the resonance. Here on the background, we have the FLI map with the initial conditions given by the center of the distribution. And you can see that these points dance around with the resonance. And at some point, they start to diffuse along it, and you can see that some points will go with to high values of the eccentricity, while others will stay low and will not re-enter. So this shows the dependence even just on the actions. And well, let's wait for it to finish. You can see really the diffusion along the resonance here. We're very close. So, wrapping up, we built an integrable model which is useful to understand the structure of resonances, including their width and the shapes that we find in the FLI map. And also we understood the dependence on the FLI cartography from the angles of small omega, big omega, and the omega of the moon. So the combination of the argument of LG and the node of the particle gives us the value of the resonant angle, which in turn determines the scanning direction of the entire phase space, which gives us the structure of the FLI map that we see. The node of the mode determines the shape of the center manifold, and the angle omega gives us the position along the tori of the center manifold, which in turn gives us the position of the resonance. Here on the bottom, you can see on the left the, say, theoretical width of the resonances in inclination semi-axis plane, and on the right, a 3D representation of the resonance increasing in width with the altitude on the z-axis, and moving along the tori of the center manifold in the plane inclination omega. With this, I have a presentation, and thank you very much for listening.